Hello everyone, welcome to class. In our last lecture, we created the mathematical foundations for what we are going to talk about today, which is RSA. RSA is a public key crypto system, and we are going to introduce two public key cryptography systems first. Then we are going to talk about the RSA algorithm itself and its speed up techniques. RSA by itself is really, really slow, so we need to speed it up. Then we are going to look into attacks on RSA, which is going to inform our understanding how long RSA keys need to be in order to be safe. And finally, we are going to conclude by showing the correctness of the RSA. So we are going to provide a mathematical proof that RSA is actually correct. So let's get into the introduction to public key crypto systems. So public key crypto systems are also called asymmetric crypto systems. And to understand those, it's best to compare them to symmetric crypto systems. So with symmetric crypto systems, we are already familiar. We covered its most prominent representative, which is AES. So in such symmetric crypto systems, when Alice wants to send Bob a secure message, what Alice is doing is she is going to use a key, encrypt the plain text, and sends the ciphertext over to Bob. And the thing here that is important is that Bob uses the very same symmetric key in order to decrypt the ciphertext and retrieve the plain text. So this is basically the hallmark of symmetric crypto systems, that the very same key is being used for encryption and decryption. And you may remember how AES worked. We had on both sides, encryption and decryption, we had the identical key schedule. And remember that this key schedule was the algorithms that allowed us to derive subkeys from an original key. And those were totally identical. And on the decryption side, we needed to reverse every step that was done on the encryption side. So this is very different with asymmetric crypto systems that RSA is a very prominent example of. So with asymmetric crypto systems, what you have to do is you have to first generate a pair of keys. And the pair of keys we call a public key and a private key, which basically reflects the role that these two have. One key is published, and one key is being kept private and secret. So Bob creates that pair of keys, and then he sends over or just publishes his public key. So publishing means that the key can be written on the back of the car, being put on Bob's public website, and so on. So if Alice wants to send Bob a secret message, what Alice is doing is she is going to use the public key in order to encrypt the plain text, and then she sends over the ciphertext, and on the other side, on the decryption side, Bob is going to use his private key in order to decrypt the message and retrieve the plain text. So the big advantage is that you can actually publish one key, one part of the two-part key. And anybody who wants to send a message to you can use that very same public key. Once the message is being encrypted with the public key, nobody can decrypt it. So if you are communicating, let's say, with n participants, n different people, you only need one pair of a public and a private key. Otherwise, in symmetric crypto systems, what you need to have is you need to have n different keys. So the number of keys is actually being reduced dramatically in asymmetric crypto systems. So in general, what public key crypto systems are out there? Well, the most prominent one is RSA. There are, however, a number of others, but it's just pretty much like a handful of public key crypto systems, which comes as a surprise because there are hundreds of different symmetric key cryptography systems. So RSA is one of the most prominent public key crypto systems, but there are others as well that we are all going to cover, except these two here, and I'll comment on that in a second. Anyhow, a number of public key cryptography systems rely on the discrete logarithm problem. This is first of the very first one actually that was a public key crypto system is Diffie-Hellman. Diffie-Hellman is being used for disseminating keys. Al-Gamal is another one, and DSA digital signature algorithm. So a variation of the discrete logarithm problem is actually elliptic curve cryptography systems. So we are going to cover here in our class, we are going to cover RSA. We are going to talk about discrete logarithm problem and the generalization of it. And as a consequence, we're going to talk about elliptic curve cryptography. And we are starting out with a discrete logarithm problem covering Diffie-Hellman. However, these two, Al-Gamal and digital signature algorithm, we are not going to cover. So Al-Gamal, we are not covering at all. However, we are going to look into DSA in our follow-up class, which is Cybersecurity 403. Okay, so we are going to look into DSA there. Okay. So let me get this back to normal. All right. So some fun facts about RSA. RSA was invented in 1977 by Rivers, Shamir, and Edelman. These are three really sharp guys from MIT. And one of them is actually a co-author of the algorithms book that we are using in 421. So those are really famous people. And by the way, they are also very rich people because of their invention here. So RSA is the most popular public key crypto system. And as I already said, there are only a handful of such algorithms. It was patented in the US, but the patent expired in 2000. So one thing that may come as a surprise, RSA is very computationally intense, which means that it is not actually used for general encryption, decryption purposes of plain text, as is the case with symmetric algorithms. So what we do use RSA for then is actually to use RSA for key transport. So basically what that means is that you use a public key crypto system in order to transport symmetric keys. And symmetric key cryptography is way more efficient, as I already said, than public key cryptography. It's computationally way less intense than RSA. So we also may use it for digital signatures. Okay, so those are the most prominent two use cases for RSA. So let's talk about the RSA algorithm itself. So when you work with symmetric key crypto systems, all you need to do really in the setup is to create a random number, which is going to serve as the symmetric key. And the random number needs to be sufficiently large, of course, like 128 for AES in the usual case. Here with RSA, it's different. We have a key generation phase, and the key generation needs to be done very, very carefully. So we actually compute our keys. So we compute our keys in order to retrieve a pair of public-private keys. So this is very different from what we know from symmetric key crypto systems, where you just choose a random number that is big enough and then you're done. So here we are going to compute our key pair. So how is that being done? Well, the computation for the private and public keys is being done in 5 steps. The first thing that we need to do is we need to choose 2 large prime numbers. And these prime numbers need to be distinctly different, need to be really much larger than 512 bits each. And the reason is that the security of RSA relies on the difficulty to prime factor a large number. And what can be done these days with quite a bit of computing resources, we can prime factor numbers up to 1,000 bits. So as you have seen in the past, that the security level, the number of bits in the end that you use depends on the best known attacks. And you may remember that from the hashing that we had to double the length of the key in order to be safe. So this is true here as well. So given that we have attacks that can factor, the only known attacks that can factor a large composite number into primes, and we can do that up to 1,000 bits. What is recommended these days is to choose P and Q to be around 1,000 bits each, so that the product of the two is about 2,000 bits or even higher. So that's the first step, choosing 2 large prime numbers, which is already pretty involved. And we're going to talk about that later on in this class. So once we have those 2 prime numbers, we are going to compute the product of these 2 numbers. And we call that product n. So throughout the literature describing RSA, you know, all of these names, P, Q, N, and we are going to see E and D, um, all of these are pretty much standardized and used across the board. So N is in red here because this is the first part of the pair key that we are about to generate. So N. In the third step, we are going to compute phi of n. And remember, phi of n is the number of elements in ring n that are relative prime to n. So you saw how phi can be computed algorithmically. What we actually need to do is we need to have the prime factorization, and then we can come up with a product that looks something like that. Here in this case, of course, we know what the prime factors of n are because we computed n already out of two prime numbers. So we can compute phi of n with little effort. All it takes is, you know, the different exponents of p and q and pretty much all of the prime numbers of a composite number. But here in this case, we only have two primes. So n is a product of p and q, two primes. And each prime has the exponent of 1. So we have 1 here, and 1 here. And we have p to the 0 here, which is 1, and q to the 0 here, which is also 1. So in other words, computing phi of n is really easy to do. So in the next step, we choose our what is called a public exponent, or basically the public key, the second part of the public key, which we call E. So E stands possibly for encryption. So and E is being chosen out of numbers 1 through phi of n minus 1. So in reality, I said already that RSA is computational intense. In reality, you try to keep E relatively small without compromising security. So we're going to keep it small. It could be 3 actually, or it could be 2 to the 16th plus 1. Those are the two choices which, for the most part, are being used. So there are concerns about E being just 3. It's not considered to be totally safe, but to the best of my knowledge, nobody could actually prove that so far. So we need to choose E in a certain way. Specifically, it needs to be relative prime to phi of n. So in other words, the greatest common divisor of E and phi of n needs to be 1. And the reason for this is that the inverse of E exists. And you remember that a necessary condition for an inverse to exist is that in a ring N, an element needs to be relative prime to N for its inverse to exist. So of course here we have phi of n. So one of the difficulties here is to not mix up phi of n and n. Okay. So in the fifth and last step, what we're going to do is we are going to compute the private exponent d, and d stands for decryption. So D is the inverse of E, which means that D times E is congruent 1 modulo phi of n. Okay, so which is pretty much what we have already learned before. This is the very way how an inverse is being defined in modular arithmetic. So with that, we have two pairs of keys. We have a public key, which is comprised of n and e. So again, both of these are public. So an attacker knows n, an attacker knows e, and the difficulty for the attacker is to factor n into prime numbers, into two prime numbers if n is really, really large. So remember that in the very first introductory lecture that I said there is basically the middle ground that we choose between very, very primitive ciphers, which have been historical ciphers, and the one-time pad, which guarantees 100% safety. There's middle ground. So we choose a smaller key as opposed to having a key length that is the length of the plain text. So we choose a smaller key and we compromise, we give up on security. So here in this case, you see that quite clearly because given unlimited computing resources and unlimited time, RSA is not secure at all. Okay, you can always, with unlimited resources and unlimited time, you can factor n into its two primes, and then that is the way how to crack RSA. So I just wanted to mention that for your understanding, because it's just interesting. So then we have the private key. And the private key is comprised of n, of course, which is also public. So the real secret is D. Okay, the real secret is D here. And that's the reason why in literature you see that very often that the private key is just being is just said to be D. But when you think about it, the way how you run the algorithm, you need, in order to decrypt, you need n as well, as we're going to see in a second. So really the private key is both n and d, while d is the only part of the two that is actually secret. So this is the algorithm to compute those two keys. So a few remarks here. Given n, and I mentioned that already, P and Q is computationally infeasible these days if P and Q are sufficiently large. And I mentioned already that these days P and Q should be on the order of 1,000 bits each. So if the attacker knows phi of n, the attacker can compute the private exponent. Why? Because the attacker needs to use this formula in order to retrieve D. And if phi of n is known and E is known because it's part of the public key, then D can be computed with no problem at all. So phi of n must not be known. But what we're going to see is, and what you see already here, phi is not contained, phi of n is not contained in either the private key or the public key. So phi and phi of n plays a role in the underlying functioning of RSA itself, but it's not being used explicitly anywhere. It's just being used in the setup phase. So we are going to see that the very functioning, the correctness of RSI relies on phi of n and Euler's theorem using phi of n. So the other thing to know is that both E and D are mathematically totally equivalent. So there's pretty much no distinction between the two, mathematically, conceptually. In reality, however, they distinguish by two things. They distinguish by way how the protocol is being handled. So one is being defined as private, the other is being defined as public. And the other distinction is that E is sufficiently smaller than D. So E is much, much smaller than D, and this is for efficiency reasons. Okay, so how does the RSA encryption and decryption work? So the encryption, obviously what you have is you have a public key that is given to somebody who is the sender of a message to another person who is the owner of the private key. So this is what the sender of a message has. So now the message X is being put to the power of E, that parameter that we just computed, modulo n. And this is the encryption of the plain text X, a block of plain text that we call X. So that is the encryption function. The encryption function is computed like that. So what you see from that, because of the modulo n operation, that the length of X and consequently also of Y is smaller than n. So X can only have a length up to n minus 1. Otherwise, this algorithm doesn't work. Okay. So that together with the computational cost of computing X to the power of E, and we choose E considerably small in order to make that computational cost small. But on the decryption side, we do compute Y to the power of D, which is a large number. So this cost makes RSA such a bad candidate for encryption and decryption of messages on a regular basis. So I jumped ahead already a little bit. So you see that the decryption works the very same way as encryption, except that we use, the private key, the D, we use for decryption. So you see that up here, it's the exponent. But the way how the plain text is being derived is the very same way how we derive the ciphertext in encryption. We take, instead of the plain text, we take the ciphertext to the power of D modulo n, which turns back, which allows us to retrieve the plain text X. So again, keep in mind, because of the way how the algorithm works, we are limited to a size for the message of smaller than n. Okay, so here's an example how This works for small numbers. Of course, these are so ridiculously small that we do not have any security at all. So we choose P to be 3 and Q to be 11. In reality, these need to be huge numbers. And just finding primes, really, really big primes, is a problem by itself that we are going to cover in a minute further below. So obviously, n, the product of the two, is 33. And we compute phi of n. Phi of n is p minus 1 times q minus 1, which is 2 times 10, which yields 20. Okay. So we choose E to be 3. Remember that it needs to be relative prime to phi of n, which is the case here. And we increase the chances that E is relative prime to phi of n by choosing a prime here. Okay, so in reality, E actually may be 3. So you see the secret of E is it's not a secret, it's a public key anyways, and it can be small. It can be ridiculously small. The secret is really in the n, that is the factor of 2 primes, which are unknown or hard to figure out normally. So the other way of choosing E, which is very popular, is to choose 2 to the 16th plus 1. And this has to do with the fact how we can efficiently do exponentiations, which we're also going to cover further down. So, and convince yourself that 2 to the 16th plus 1 is a prime as well. So now that we have E and E is relative prime to phi of n, we can actually compute D, which is the inverse of E. And here in this case, the inverse of 3 mod 33, mod 20, sorry, is 7. So we can check that. We can say, okay, D times E, which is 3 times 7, is congruent 1 modulo 20, which is the case, as you can see here. 7 times 3 is 21, modulo 20 is 1. Okay, so now Alice receives Bob's public key, which is n. So n, remember, and not phi of n, and E. So this is what we are going to send over to Alice. And Alice wants to send the important message of x being 4. So our plain text is 4. So remember that we need to raise the plain text to the power of E modulo n, which in this case is, as you can convince yourself, 31. So, and also note that n is 33. So both x and y are smaller than 33. So on the receiving side, Bob is raising the ciphertext to the power of D modulo 33, which is indeed 4, as you can convince yourself. Okay. So what I did is I used equivalency classes here, modulo 33 equivalency classes. So 31 to the power of 7 is quite a large number. So the equivalence, a equivalent value of 31 is minus 2. So remember that, any number with the same distance of the modulo number, here in this case, from minus 2 up to 31, it's a difference of 33. All of those numbers that have the same difference belong to the same equivalency class and can be used equivalently in any modulo operation, which is really interesting. So in this case, we use that because it's much easier to, mentally do the math for minus 2 to the power of 7 as opposed to 31 to the power of 7. So, and this, if you do the mod operation correctly, results in a plain text of 4, which is the correct result. Okay, so this is how RSA works for small numbers. So, but in reality, we have huge numbers. And the problem in practice is that we need to raise both the plain text and the ciphertext to the power of huge numbers, modulo n. So we have exponentiation with very, very large numbers. And in order to make that computationally worthwhile at all, we need to have some speed up techniques. But even with the speed up techniques, RSA is slow. And I mentioned already that you use basically RSA, you can use for distributing symmetric keys. And then you actually use a symmetric cryptosystem like AES to do the real encryption and decryption of messages. So, speed up techniques. How can we speed up that exponentiation? On the encryption side, what we can do is we can use a short public key, a short public exponent E. And I mentioned several times that could be 3, that could be 2 to the 16th plus 1. Both are prime numbers, and both are popular choices. Sorry for this thing jumping back here. So obviously exponentiation with a relatively short base, with relatively short exponent, sorry. And the base is, the plain text. So that makes encryption already way faster. Okay, so where we cannot make any compromises is the length of D. So on the encryption side, we really do have a problem. D is going to be large, very, very large. So exponentiation is going to hurt with a large exponent, no matter what. So one way to speed up this is based on what is called the Chinese remainder theorem. So what that comes down to, instead of doing exponentiation with one large number, what is being done here is to do exponentiation with two smaller numbers, basically with pi and q that we had before. Because as you remember, on the decryption side, sorry, not pi and q, p and q. So Bob knows what p and q are and can use the Chinese remainder theorem to basically, instead of doing exponentiation with one large d, he will be doing exponentiation with P and Q, which are much smaller numbers, of course, and that way speed up the decryption. But still, we have exponentiation here as well. So the exponentiation is still needs to be done with two relatively large numbers. It's just that they are considerably smaller than the original number, which is D. So, in other words, we need some form of fast exponentiation, which is important on both sides, both on the encryption and the decryption side. Okay, so we're going to talk about that. Before we talk about that, let's first cover how to find large primes. So you remember that we need to have a P and a Q that are really, really large prime numbers. So how can we find prime numbers? Well, we could, just have a random number generator generate numbers, and we factor those into primes. Well, wait a minute. That was the very premise and the promise of RSA securities. So factoring composite numbers is not an option. So we need to have a different workflow. What we do is we just generate numbers with a random number generator, and then we check whether those numbers are primes. Okay, so we apply a primality test. So some research has been done how dense prime numbers are, and it turns out that prime numbers are losing density the higher the bigger the numbers are. So in ranges of huge numbers, there are a smaller number of prime numbers compared to ranges of numbers that are relatively small. So the biggest numbers of primes you have in the range of 1 and 100, and that density is going down. However, prime numbers are infinite. So we have an infinite number of primes anyways. So you can prove that by contradiction, and it's relatively easy to do, and I don't want to do it here. Anyhow, research shows, the prime number theorem that the probability of P dash being a prime is 2 over the natural logarithm of P dash. This is what the prime number theorem says. So obviously, the larger this expression is, and it becomes larger very, very slowly, I have to say. The larger this expression is, the smaller the probability that P dash is a prime. So for concrete numbers, obviously it has to do with the length of P dash. So the longer P dash is, the less the likelihood that it is actually a prime. So for 500-bit random numbers, odd random numbers, the likelihood that it is a number in that range at that size is prime is 1 over 177. So what that means is it takes about 177 times to try to check a number until you actually have hit, at the average, until you have hit a prime number. So 177 trials, trying 177 numbers at the average in order to find a prime number at that size. And as I said, because we have the natural logarithm here, if you increase p dash, the resulting expression grows relatively slowly. So we are not going to run out of prime numbers. That's what it actually means. Okay, so what we do, this gave us the scope of the computation that we have to do if we check for for primes, you know, among really large numbers like 512 numbers upwards. So roughly speaking, you may need to try like 200 times in order to find one prime number, which is not too bad with the computing power that we have these days. So uh, once we generate all of these randomly generated numbers, now we need to check whether they are prime. So what we can do is, on the face of it, remember that Fermat's little theorem, um, the modular number here is prime. It needs to be prime for Fermat's little theorem to hold. So on the face of it, we could use, you know, if we transform Fermat's little theorem, and we assume that p dash is a prime number, we can come up with different a's and check whether the Fermat's little theorem actually holds. And obviously, we need to check many, many times. So the more numbers a we come up with, and this is actually our security parameter, the higher the likelihood if we do not run into a contradiction. So if our computation provides anything other than one, we know that p dash is not a prime number. So there's a glitch, however. There are very, very rare numbers. So the likelihood to hit such a number, you know, and check it, such a number p dash, and check it is very, very rare. But there are numbers out there that are composite numbers and actually do fulfill Fermat's little theorem. So that's unfortunate because Fermat's little theorem, that's what it means, cannot be used in the general case for testing for primality. So obviously, Fermat's little theorem holds in general if p dash is prime, but unfortunately there are numbers, they're called Carmichael's numbers. Carmichael numbers are composite numbers that also fulfill Fermat's little theorem. So in reality, what is being done is to use the Miller-Rabin primality test. And I'm not going to cover it here, but if you're interested, have a look at the book in chapter 762, where Miller-Rabin is being described, or anywhere else if you Google for it, of course. All right, so now that we have a relatively efficient way of finding prime numbers, so now working with these prime numbers, And we derive, remember, E and D out of that, and E and D are exponents in our encryption and decryption algorithm. So this is slow. And what we are discussing here is a technique called fast exponentiation that reduces the computational load to do exponentiation by a lot. So we are talking from linear runtime to logarithmic runtime, which is considerably smaller compared to linear runtime. So if you took an algorithms class, the surprising thing here is that normally we are happy in the realm of algorithms. Normally we are happy to have a runtime for an algorithm that is linear. However, cryptography is a very special field, and we try to make things as hard as possible. So a linear runtime in the context of cryptography may not be a good runtime after all. So, okay, let's look into a few examples to show how fast exponentiation is being done. So let's do it first as in its unrefined form. Let's do exponentiation with no speed up. And the example that we are looking into is actually to compute x to the power of 4. So the unrefined way, what we could do is we could um, compute x times x, which is x squared. And then we compute x squared times x, which is x cubed. And then we compute x cubed times x, which is x to the 4th. So what we did here is we multiplied the former result by another x. So we added x linearly as a factor to the end result. And this is a linear runtime, obviously. So the other way how to do it is we compute x times x, which is x squared. Now we know that x to the 4th is x squared times x squared. So in other words, what we do here is we compute x squared times x squared. And you see that instead of 3 computations here, we had only 2. So if we project that example into really large numbers, this advantage, this gain in computational load, or getting rid of computational load, is going to be enormous. So let's look into a more realistic example. So let's look into have an exponentiation of x to a number that is a 1 and 1024 bits after that 1. So if we, in this case, 2 to the 1024 is a 1 and 1024 zeros. So if we do that in the primitive way, adding factor after factor, we have 2 to the 1024 minus 1 multiplications. This is, of course, a huge number. So the number is so huge that it exceeds by far all of the atoms that we have in the known universe. So even if we turn our whole universe into chalk, we cannot write down the result of this computation, and because it's just way too few chalk atoms, and of course we wouldn't have a blackboard either because we turned the whole universe into chalk. So in the way how we did it on the other end here, um, by continuously grouping factors with higher exponents, um, we get a totally different result. So instead of 2 to the 1024 minus 1 multiplications, we actually have only 1024 multiplications. So let's see how that works. So remember, in the beginning, we start out with x times x. So this is x to the 2. If we rewrite the exponent to something at base 2, this is, of course, 2 to the 1. Okay. So now we multiply x to the 2 times x to the 2, which is, at the exponent level, twice that exponent. So which is x to the 2 to the 2. Okay. So if we go on like that, and again, we multiply x to the 4 times x to the 4, which is actually, as we know, x to the 2 times x to the 2 to the 2. This is x to the 3. So what actually happens is here the exponent of the base 2 here is increased by 1. So with each of such computations, with each step, the exponent is only growing by 1, which means that every time it grows, we have 1 multiplication. In turn, that means that we have only 1024 multiplications, which is so much less than having 2 to the 1000 multiplications, essentially. So while this part is not feasible at all, this part is quite doable. Okay. So there's only one glitch. What we have been doing so far is simplistic. We have made an assumption. We have made the assumption that our exponent is a power of 2. So how can we expand upon that idea and have a fast exponentiation algorithm that is valid for any exponent, that can be used with any exponent? So what we need to do is we need to generalize our idea for any exponent. And the resulting algorithm is called the square and multiply algorithm. Okay. So the squaring we have already seen, and we see that every now and then we need to throw in a multiplication as well. Okay. So we start out with an example. And the example is to raise x to the power of 26. And we saw already that basically we have to deal with with binary, we double the exponent here. So we have to deal with binary operations. So it may be beneficial to just transform the 26 into a binary number. Okay. So I have already jumped the gun and I showed what an efficient exponentiation would look like for 26 so that we can see how a general purpose algorithm could be derived from that. So you see that x to the 26 is x squared. Then we multiply x squared times x, which is x to the third, x cubed. Then we square x cubed, which is x to the sixth. Then we square x to the sixth again, which is x to the 12th. And then we multiply x to the 12th times x, which, is x to the 13. And then we square again x to the 13, so which means that the exponent is being doubled, which is x to the 26. It's exactly the exponent that we were shooting for here. So you see that the exponentiation algorithm here is a mixture of multiplying and x squaring. Okay, so how can we distill from this an algorithm that is can be applied in the general case for any exponent? So what you see here has two parts actually. One part is the actual computation that we need to do. So obviously we need to square, which is for large numbers, computational intense. So we have to square and we have to multiply. So what you see on the other end, however, on this side here is what that squaring and multiplying is actually doing in terms of the exponent that we are having. So remember that we try to shoot for getting an exponent of 26. And the idea is that with each squaring, the exponent at the time is being doubled. And if we are multiplying, we add 1 to the exponent. So in other words, the mixture of squaring and multiplying in order to compute the final result resolves into doubling the exponent for squaring and adding 1 to the exponent for multiplication. So let's see how that works here. So the direction that I put here is actually the same direction of the computations that we do here. That's the reason why I have that arrow here. So when we start out just squaring x, okay, we're here. So here actually, this is the computation that we do. If we resolve that into, what happens to the exponent for base 2, it means that we had an exponent that was 1, and doubling is shifting actually of the 1 to the left. So we go from 1 to 1, 0. You see that here, 1, 0, base 2. Whoops. So obviously our squaring led to recomputing the exponent by just shifting it to the left by 1. So the next one was the multiplication. We are actually here, okay? So we multiply x. What does multiplying do? So we multiply x squared times x, which is x cubed. So what does that do on the exponent side here? As I already mentioned, it means that we add 1 to the exponent. Okay. So now it's actually easy. We see that we square twice. So we square here, which is squaring here and here, doing these computations. So here, after we squared, we have x to the 12th. Okay. So pretty cool. What does it do? Again, it just shifts our exponent twice. So we added 2 zeros. Each squaring added a 0. So let me take this back here. So finally, not finally, next step is we multiply by x. So what does it mean here? It means that, the multiplication by x, from the x to the 12th, we go to the x to the 13th, which means that we add 1 to the exponent. Here's the one that we add. See, we had a 0 here, we have a 1 here. We add 1 to the exponent. All right. And finally, eventually, we square one more time, which is here, which takes us from x to the 13 to x to the 26th. And this again shifts our binary number. So we add a 0 one last time, which is this 0 here. Okay. So what you see, the number that we have here is exactly our exponent that we have in decimal here. It's our exponent expressed in a binary number. So the cool thing now is that we can turn around this idea and go the other way. So what we do is we start here, we ignore the first bit, we start here. This one here obviously is a 0 plus 1. So the 0 comes from the squaring and the 1 comes from the adding, from the multiplication, which is, adding a 1 here on the exponent side. And then we go one further down and we square. And then again, we go further down and we square and we multiply. And then finally, we go down and square one last time. Exactly those operations that we did here. So what that means is that we can turn around what we did here so far, and when we have to exponentiate a number with a certain exponent, what we do is we retrieve the binary representation of that exponent. Sorry. We retrieve the binary representation of that exponent, and then we use that as a guide to find out when we need to square and when we need to multiply. Okay, so here's our algorithm. Again, the idea is the squaring on the computational side results in a shift of the exponent, and the multiplication on the computational side is an adding of 1 to the exponent. So that's the idea. And this results in a beautiful algorithm. So here's the pseudocode. What we do is we retrieve the exponent in binary representation, and then we go over all the bits from left to right. We ignore the leftmost bit because that was the original one that we had here. This one here, this is a given. Sorry. And then we square. So we square here. And whenever the bit is 1 that we look at, we also need to multiply. This is here. And we keep doing that until we have run out of bits. So sorry about the lengthy presentation of the fast exponentiation, but I hope it pays off and you understand how this works. So the basic idea was that on the computational side, whatever we need to do is squaring and multiplying, and that has an effect on the exponent side. The exponent is being shifted or 1 is added, which means that we just turn it around and we basically go from this side here and derive from how the exponent is being decomposed. We derive the actions that we need to do on the computational side, okay, on actually computing the result, which is very interesting. Okay, so let's get to attacks on RSA. So the only known attack on RSA mathematically, there are other, side channel attacks, there are attacks on the protocol, but attacks that really concentrate on the mathematical soundness of the algorithm. Those attacks are only based on the idea of decomposing our composite number n into 2 primes. And this is still really, really hard to do. Okay? So if an attacker knows P and Q, the attacker can easily compute phi of n. And with phi of n, the inverse of E can be computed and the secret exponent can be derived. But again, the only known attack to do this is to use factorization. And at this time, it's only possible to factor in a large number into primes up to 1,000 bits. And this is already quite a stretch. You need quite a few computing resources in order to do that. But still, in order to future-proof your, private public key pair, what you should do is you should use an n that is at least 2,000 bits, if not 4,000 bits, which means that we have to have two prime numbers which are 1,000-bit or 2,000 bits long each, which of course does not make the exponentiation any faster. Okay, so I provide a link here about factorization records which have been established so far. So there are no other mathematical attacks that we know of. Maybe somebody out there's a suspicion that there may be a shortcut, but nothing has been found so far officially. So the mathematical foundation of RSA seems to be relatively stable. Okay, so let's get now to the very last step and prove the correctness of RSA. So we start out by pointing out that the decryption of a ciphertext is basically done by raising the ciphertext to the power of d modulo n. And remember that our ciphertext came to be by encrypting the ciphertext, which is being done to raise x to the power of e. So what that means is that those two things together, x to the e times d modulo n, needs to be x. So this is a very, very question that we need to show. This is a question at this point. Is e to the x to the ed, is that really x modulo n? So we wanna show whether that question mark here is justified or not. So, and should be turned into an exclamation mark, and we can show that actually. So the proof relies greatly on Euler's theorem, which involves the phi of n. And what you see here is the reason the proof actually shows you where the phi of n comes into play, because before it was kind of strange. Why do we care about the phi of n when all we care about in the encryption and decryption is really n? So all of the modulo operations were being done modulo n. And it's actually here in the proof where it becomes clear that the phi of n plays such an important role. So, and we see that already in the two steps that we need to take in order to prove. And those steps have to do with the applicability of Euler's theorem. So, which really comes down to the question, is x relative prime to n or not? So remember, x is a plain text, so it could be anything. So it could be conceivable that x is not relative prime to n. And then Euler's theorem is not applicable. And that's the reason why we need to, for that rare case that x is one of the factors of n, so which means that x is a multiple of either p or a multiple of either q. In that rare case, we have a second part of the proof where we need to prove for that case specifically. So remember that the way how we derived E and D, it really had to do with the fact that E and D, D is actually the inverse of E. So E times D is congruent 1 modulo phi of n. This was our very way of actually computing when you look up there how we derived the keys here. So what you see here is what we did in step 5. So we needed to choose d such that E times d is congruent 1 modulo phi of n. So you see that's where the phi of n comes into play again. So this is a given. This is what the algorithm relies on. So we can obviously rewrite that into something what actually modulo means. Okay, modulo means that phi of n divides ed minus 1. Okay, or E times d is equal to 1 plus a factor times phi of n. Because if we compute ed minus 1 and we say that ed minus 1 is divisible by phi of n, this is the number how many times phi of n goes into ed minus 1. So in other words, this here is just a rewritten form of this. It expresses in concrete mathematical terms what that somewhat fuzzy notion of congruence actually means. Okay, so and this is some whole number. The t is some positive whole number. So once we have that, we can rewrite. Remember, we are interested in the expression x to the power of ed. So if we put x underneath here as the base, this is what we get. Okay. So we can raise x to the components that we have here, which results in this expression. So and this expression here, this one, we can rewrite to say that. Okay. So consequently, if x to the ed is equal to this, and we expect that x to the ed is actually only x, what that means is that this expression needs to be 1. So our proof comes down to proving actually to show that this expression is 1. Okay, so how can we do that? Well, let's remember Euler's theorem, which states that if x is relative prime to n, and this is the reason why we had that first case, x relative prime to n. Otherwise, Euler's theorem is not applicable. So if x is relative prime to n, then x to the phi of n is congruent 1 modulo n. So if we raise the whole thing to t, what we get then is, on the left-hand side, this original impression to the power of t. On the right-hand side, however, we get 1 to the t, which is still 1, regardless of how big t is. So what we have shown is that this expression, that this expression is really 1 modulo n. Whoops. Sorry again. I love OneNote. So remember where we came from. We needed to show that this here is 1. And with applying Euler's theorem, we actually could show that. Which means, in conclusion, that x to the ed is actually x modulo n. So this is the first part of the proof. Okay. The second part of the proof is where x is not relative prime to n and Euler's theorem is not applicable using mod n. So how can we prove RSA to be correct in that case? It's a rare case, but we need to still care about this case because it's a possibility, as x could be anything. So if x is not relative prime to n, what that means is that x and n share a factor. And because n is comprised of the product of two prime factors, x needs to be a multiple of either of the two. It cannot be both because x is smaller than n, as we have shown before. So in other words, x is just some factor of p or q. That's what you see here. So let's just assume, without limiting generality, that x is a multiple of p. And it doesn't matter whether it's p or q. So a multiple of p, and that multiple is, we want to call it r. Okay, a whole number. So x is r times p. So once we say that, it becomes clear that x is relative prime to q. Of course, because they do not share a factor other than 1. So which means that Euler's theorem is not applicable to x and n, but it's applicable to x and q. So in an integer ring Q, Euler's theorem holds in this way. X to the power of phi q is congruent 1 modulo q. So let's keep that intermediate result. So remember the expression that we were interested before? This guy here needed to be 1. Remember that? So we have it up here. So this needed to be 1. So we need to look into that again. But this time in the context of x not being relative prime to n. So now we deal with that expression and we decompose it. So remember that phi of n is p minus 1 times q minus 1. This is just what phi of n is. You can look it up in the steps of how we created our keys. So now the interesting thing comes. We have q minus 1 here, which is in integer ring q, the way how to compute phi of n. So in integer ring q, and q being prime, q minus 1 is phi of q. The one is actually here limiting the zero, um, which has not a, a greatest common divisor of one when you look at q and zero. Okay, so zero can be divided by q, q can be divided by q. So zero is not relative prime to q. That's the one that we need to subtract here. So interesting enough, with that approach, we can replace this part here with phi of q. So, and we throw mod q in here. So we can take the mod q of this, and what we get here is we take this out here. This becomes t times p minus 1, and we have that nice compact expression here for the x to the phi of q, and this is to the power of t times p minus 1, which is very interesting. So because we can replace this and apply Euler's Euler's theorem here, 2 to the t again, this becomes 1. And again, we have mod q here. So very interesting. Not quite where we want to be at, but quite a bit where we want to get. Quite a bit towards that that direction. So what's the result now? The result is that we have this is congruent 1 modulo q. Okay, so this is the result. Very interesting. Not mod n, mod q. So we apply the old trick that we used above here, and we rewrite the mod q into what it actually means mathematically. So it means that the expression on the left, minus 1, is divisible by q. So q goes in there a number of times, which we call u here. Okay. So again, this expression, minus 1, is divisible by q. So q goes into the left-hand side minus 1 a number of times, and that number of times is u times. Okay. So now let's get back to the original expression that was valid, where we showed when x was, relative prime to n, we could show easily that this is 1. It's not that easy here, but let's start at this point here. Okay. So in other words, the expression that we have here, this expression, we multiply by x. So which means that we multiply this expression by x, which is equal to this expression. So this expression, we multiply by x and get this. Okay, very interesting. So again, this is this. So we need to multiply this by x, and we get this. Just want to make it really clear. So now we can decompose this expression and say, okay, x is actually r times p. Now we see p here and q here, and they are factors. Well, wait a minute, p times q is n. Okay, so this is n. So what we really have here is we have n times a factor, which is r times u, we don't care, plus x. So if we modulo n this, and this is what we need to do anyways, when we have x to the ed, it's modulo n. So which means that this is the same as this, and this is congruent to this expression modulo n. What does that mean? It means that taking this modulo n means that we have modulo x plus modulo n of this expression, which is obviously 0 because we multiply n by two whole numbers. So in other words, this expression goes away. And what stays is that we have, so this goes away, and we have x here. So ED is congruent x modulo n. So we arrive, not surprisingly, at the very same result that we got here above, where x was actually relative prime to n, except that here in this second case, we needed to jump through a few additional hoops in order to show that the same premise that we had before here also holds. So this concludes our quad era demonstrandum, what we needed to prove. This concludes our proof of correctness of RSA. Thank you, guys. Thank you very much for chiming in and for bearing with me. I hope you found the lecture interesting. And in the upcoming lectures, we are going to dive into the other big area, which is the discrete logarithm problem and how we can construct cryptosystems out of the discrete logarithm problem. So RSI is somewhat unique in its reliance on the hardness of prime factorization. None of the other crypto systems that are public key cryptography systems rely on that. They rely on the discrete logarithm problem. And this is what we are going to cover in the remainder of this class, actually. So stay tuned, and I see you in the next class. Thank you very much for chiming in and for listening.